Alright, so Gauss's law is kind of all important for electrostatics, um, and its counterpart in magnetism is Ampere's law. It can help you through a lot of situations. So what Ampere's law says right now is integral of B dot dl is equal to mu naught I enclosed. So just like Gauss's law, we need a surface to work with, rather a curve. But in this case, instead of enclosing a volume, we need to just enclose an area. So whereas Gauss's law, you would use something like a cube, a sphere, a cylinder. Here we want like a square, a circle, something like that. So let's look at the simplest case, just a circle. So you have to pick a direction to go around in. For physics C purposes, it doesn't really matter what you choose ever. You just have to use right-hand rule at the end to figure out what your sign should be. So you go around in a certain direction, and as you go around each little chunk of length, that is your dl, pointing in the direction that you're walking along in. So what Ampere's law says is if you go around this little loop and you add up all the B field pointing in the direction you're walking, in other words, all the B field pointing around in this circle here, that is equal to mu naught, which is just a universal constant, times I enclosed, which is to say the amount of charge, or rather the amount of current that's flowing through the center of this surface. So here you would actually use right-hand rule to figure out which direction said current has to be. So hopefully this makes it clear. I'll try to make it clear which direction exactly this is. Hopefully this makes it clear. So in this case, I'll do it like this. Yes. So if you point your thumb along the direction of the current, your finger should curl in the direction of the dl if you want a positive product. Alright, so at the end of the day, Ampere's law just lets you figure out the B fields from flowing current. So really the most common case, and the only case I can really think of that you would want to use this, is when you have some wire with some current flowing, and you want to know, I suppose, okay, I'll draw this from a different angle. You want to know what is the B field at some distance away. So this is your wire with current flowing into the page, and some radius r away. You want to know what's the B field strength. You'd use the right-hand rule to figure out the direction, which is down. But what is the magnitude? So what we're going to have to do is we're going to draw an Amperian surface. I'll use green, which includes your point on its edge. I don't like the circle I've drawn here, so I'm going to redraw it. But you just draw a circle that includes your point. Good enough. And then you write your Ampere's law. B dot dl is equal to mu naught I enclosed. So since this situation is obviously radially symmetric, we pull B out since it's not going to be changing as you go around the surface. And of course the dot product, you know the B field must be parallel to the circle at all points since it's, again, radially symmetric. So you have this equation, or this situation here. I'll just sub in I for I enclosed. And then your integral dl is just the circumference of the circle, which is 2 pi r. And with that, you've just derived B sub r, which says B is equal to mu naught I over 2 pi r. And there you have it. That's how you use Gauss's law, or not Gauss's law, rather Ampere's law. Just draw an Amperian surface, do your little integral, and then you'll have the B field. Hope this helps you on your AP exam.